Okay, so the section we're about to go into is all about transforming a graph. So something that I didn't do at the beginning of the last lecture, but is in the video, is we talk about kind of as a starting point, there are different key graphs. There's the x squared graph, there's the x cubed graph, and they all have different key points. In fact, I'll probably pull it up before I put you into breakout rooms. But that's the starting point. We have to understand that I'm actually going to be drawing a lot today, so I might as well start now. We have to understand that, for example, and this has nothing to do with this actual problem, but the f of x equals x squared graph. That graph we see a lot in mathematics. And not necessarily specifically just the x squared graph. I mean, we do see that a lot, but also we see that x squared graph being moved to the left and being moved up and being stretched and shrunk and flip and all of these kind of different iterations. And so it's important to know not only the shape of the x squared graph, which I imagine some of you know it's kind of that U, but also to know some of the points that are on that x squared graph. So for example, as we can see here, one of my points is 0, 0. One of my points is 1, 1. And one of my points is negative 1, 1. So as mentioned in the video, I have kind of one big graphic that would be good to take down, maybe even put on a note card. Wait, don't put it on a note card because I'm only probably going to use 2 of them on the exam, but certainly something to keep in your notebook so that you can reference it and say, okay, we're transforming, which is a little bit tricky, but the first thing I need to know is what does my graph basically look like? And so once we have those starting points, we like to do exactly what I was talking about. We like to say, okay, we're not always going to have a nice x squared graph. We're going to have a lot of graphs that have that general shape. So we want to know how we would write in an equation form and how we would graph something we moved to the left, something we moved up, something we moved down, something we flipped. And so the very first transformation is called a translation. And the translation is exactly what it's kind of saying. We're not going to change this shape at all. We're not going to change the orientation. We are going to move it. Down, right, left. We're going to move it in certain directions. And how those certain directions go, and this is kind of an overall theme of these transformations is, again, let's go back to these f of x is equal to x squared graph. So if I were to find f of x plus 5, I'm not actually simplifying, but if I were to find that, that would be f of x plus 5 is equal to x plus 5 squared. So I'm kind of putting that x plus 5 inside my graph. And so when I have something happening inside my function, that is going to be left or right. Or another way to think about it, it's going to be moving some way in the x direction. It's going to be moved to the right. It's going to be moved to the left, some way horizontally. And that happens a lot with transformations. If something happens inside my function, it's going to be affecting my x values. If something's going to happen outside my function, it's going to be affecting my y values. And so specifically what this is going to do to my graph is this is going to shift it. And it's going to shift it right. Nope, sorry. Left. And now in this case, if I see something like this, well, kind of to tie it again to this overall example we see over here, that would be x squared minus 1. And notice how this minus 1 is not inside my function. I'm not squaring the 1 at all. And so if it is outside my function, then that's going to move up or down. And specifically in this case, we're doing -1 from all of them. And that means I'm going to be shifted down 1. Jackie just posted a very, very good and valid question about how do I know it's being shifted left and right? Because typically when we start to talk about these translations and we talk about up or down, it's fairly intuitive. If I'm subtracting something here, well, that probably would make sense that my graph would move down. If I'm adding something to my function, well, that also makes sense, hopefully. I'd move up, I'm adding things to it. Where this, I would argue this is kind of counterintuitive, right? If I'm saying +5, and I almost made this mistake, if I'm saying +5, well, as far as x goes, +5 should move to the right. But another trait when we're doing these transformations of this whole inside and outside is if it's inside, it tends to kind of be the opposite of what you would think. I mean, I obviously can't predict what your brain is going to think, but that's at least how mine would think. Okay, x +5 should move it to the right because, to the right of my graph is positive. Well, now if I'm changing anything horizontally, it's going to do the opposite of what I think. And that also happens when I'm doing multiplication. That happens when I'm doing division. And so if it's outside, it kind of tends to follow the thought that you would have, presumably. Again, I can't read your brain, but that's how I keep things straight. Hopefully that'll make a little bit more sense when we go through an example. Everyone good so far with just a basic starting point of translations? We're going to be moving left or right, and we're going to be moving up or down. It'll make more sense when we go through an example, hopefully. So let's go ahead and do that. So now I have this graph. This should not be a t, this should be an x. I have this graph f of x is equal to x plus 2. Yeah, so again, Jackie has the question. You determine if something moves up or down based on if it's outside of our function. So again, kind of to go back. This is outside my function. I'm doing x squared minus 1, so that's going to be the up or down. Here, it was x plus 5 squared, so it is inside the function, and that is going to tell me to move left or right. Okay, so back to this. I have f of x equals x plus 2 minus 1. Now, step 1 is to kind of find that starting graph, or identify the starting graph. So the fancy name for those are parent functions. Oops. And we try to identify them by thinking, okay, what is this before it's getting transformed? What is it before I start adding things and subtracting things and shifting things around? So in this case, my parent function is it's the absolute value graph. There are a lot of other things happening in this actual transformation, but as far as kind of what's happening overall, we see that absolute value, that's my parent function. If we saw something like if this was x cubed or x plus 2 cubed, parent function would be x cubed. If it was squared, parent function would be x squared. Okay, so parent function is the absolute value of x. Anyone watch the video? What's the general shape looking like?
Looks like a V with the origin at 0, 0.
Exactly right. It looks like a V. Okay. What are key points? What are points that I know are going to be on this parent function graph?
Isn't it 0, 0, 1, 1, and then -1, 1?
Yep. And that's kind of what I'm talking about. That's the different key points that are going to be the starting point for my graph. But it is, I don't want to say equally important, but it is also important to know that general shape that I have to the right. So that's the graphic that I'm going to need to track down somewhere. I definitely put it in the video. Maybe I'll just screen cap the video. But I put in the video all of the parent functions that might be important to us. And also they are in the textbook. Okay, so I know my key points, I know my parent functions. Now my next step is to identify what my transformations are. So I have this function overall. It's clearly no longer the f of x is equal to the absolute value of x function. So I'm going to start with just whatever's happening inside, right? That'd be order of operations. If I were to do some arithmetic on this, I would start with doing or dealing with anything in the absolute value. So what is the absolute value x plus 2 do to my graph?
Would it move it left too?
Mm-hmm. Great. Now, what is this one outside of my function going to do? Oh, I forgot my O.
Would it move down?
Perfect. Shift down 1. Everyone good with those transformations? Kind of see where they come from. We're doing that inside and outside. I don't know. I don't want to say trick, but we can say trick. That's perfectly fine. Next part of my process, write down my key points over here. My key points are -1, 1, 0, 0, and 1, 1. It's just taken from over here. So now I want to identify what my shifts will do to each of my points. So I'm starting with shift left 2. So if I'm shifting left, I have these 3 points, is that left shift going to affect my x value of the point or the y value of the point?
X value.
X value, and specifically, what is it going to do to that x value?
Would it just change each one? So the first one would be -2, or sorry, -3.
Yes, yeah. So I'm going to subtract 2 from each x value. Exactly right. And as you brought it up, the first one is now going to be -3, 1. Someone else, what's my next point going to become?
-2, 0.
Okay. Last point.
-1, 1.
Great. So I'm done with the first transformation. Now, how do I shift my points down 1?
Subtract 1 from each value.
Yep. With the x or the y?
From the y.
Yeah, we're moving down, so that means I'm going to affect my y value. So subtract 1 from each of these. And so my first point will become
-3, 0.
second point.
-2, -1.
A third point.
-1, 0.
Now I have enough information to graph. So let's kind of box those off and then graph my new function transform. So for starters, I honestly do not care what the parent function looks like at this point, because I'm going to just take my points here and I'm going to plot them. So 1, 2, 3, -2, 1, -1, 0. And then now I do care. I want to kind of replicate the shape of that absolute value graph, that V that's happening. So all I do at this point is keep the shape normal and then just make sure I'm connecting the dots. So it was a V over there. It should be a V over here. And that is going to be a transform graph. Any questions about that? Cool. And so for starters, that's what we are going to be doing in the beginning of this section. So this should get you through the entirety of that first worksheet. As I mentioned, actually, I can just pull up the worksheet. Does anyone need this still in their notes? Okay, I cannot do my clear if you do. So let's pull up that worksheet. Okay, so this is what I started with. We don't have to actually start with a specific function. These are very general. We did the absolute value graph as the parent function. So we know what the key points of this are before my transformations. So one of the big graphs, and this is honestly probably the most used parent function, is what I started that lecture with, that f of x is equal to x squared. General shape of that is this. And then my key points are going to be -1, 1, 0, 0, 1, 1. Exact same thing that we saw with the absolute value case as far as key points go. Shape's a little bit different. Key points are the same. Square root graph, so this guy. That one is going to look a little bit strange. It is kind of this parabola tilted over, but we have to account for the fact that we don't, or we need to keep it as a function. So we only draw the top part of the parabola. And then my key points are going to be 0, 0, 1, 1, 4, 2. Cool. That should get you through the worksheet. There might be 1 or 2 more parent functions you need to know for that. If you can get through 7, we will be more than prepared to finish up this section. So I don't feel too concerned that you'll need more parent functions than I just gave. Oh, sorry, I should write out what the actual parent function is for this. It's f of x is equal to the square root. Okay. All right. Now we have everything in order. This is part 1. We will get through part 2 today. It's only going to be 2 more examples, but I want you to feel good about these translations because honestly, if you feel confident with how these work, the rest of the transformations are very similar. It's going to follow the same process of identify your key points, slap those down, identify the transformations, and then say, okay, step by step, I'm going to do my shift left, shift right. I'm going to do my multiplication. I'm going to do my division. I'm going to do my flips. So it's all the exact same process. It's just, it's going to change slightly how we affect those key points. Okay. So I imagine some of you guys were like, okay, I didn't really have a whole lot of time to practice these. That's not a translation, that's a transformation. These translations, well, they're kind of part of a big picture. So we don't only want to talk about being able to move things up and down, kind of shift them around, because honestly, I feel like some of you probably didn't need that lengthy process of, okay, we now subtract all the X values and now we add all of the Y values. Because it's not too difficult if you know the transformations to say, okay, yeah, that point goes left 2, down 1, boom, that's my new spot. I can go ahead and graph it. When we start to introduce other parts of transformations like stretching, shrinking, flipping, all of those things become a little bit tricky, but they're all part of this transformation idea that we are able to shift things around and flip them and stretch them and shrink them. And sometimes we can do those all at once. And as long as we kind of stick to the process, yeah, it seems like it can get a little bit overwhelming with all of the things we can keep track of, but really at the end of the day, it is the exact same process. So I'll start my video. Writing. So here I'm trying to describe my transformation. What's the parent function that I'm going to use for this? Oh, I don't want to do that. This guy. What graph on that big set of graphs that I just showed every group would I use to start my transformations here?
Would it still be the parabola from the x squared?
Yeah, exactly, right? This is kind of big picture what's happening. There are other things going on for sure, but you don't identify that square or that cube or that absolute value. That's always your starting point. So I know my starting point, my parent function is f of x is equal to x squared. So we draw a quick sketch over here. The sketch is not super important. It doesn't have to be very accurate. The shape is very important. And what else is super important are the key points. So what are the key points for my x squared graph?
-1, 1, 0, 0, and 1, 1.
Right. Order doesn't really matter, but I actually preferred what you said, so I'll write it how you say when I go through my process. Okay, now I want to describe my transformations. And as I said when I was doing my translation, we should follow order of operations. Same type of thing with translations, though, that they're fairly simple. You don't really have to follow order of operations. You could have shifted it up and then shifted it left instead of doing the order I did. That is no longer true. When I'm doing these transformations and I'm multiplying and negatives are flying around, order of operations is very important. So order of operations, the first thing we deal with is, well, it's parentheses. So I'm going to describe that transformation right there. So what is the transformation I just underlined? In black, it might be kind of hard to see. There we go.
Shift to the right one.
Yep. The right one. Cool. Next thing with order of operations would be the square. Yeah, but we're graphing, so it's not really going to be something we do. It would be multiplication. So it would be this. Now, technically how you write that transformation is you would say that is a reflection. And since it's outside of my function, it's going to be a vertical reflection. I'm going to be flipping my graph like potentially like this. That's what that would look like. And so the fancy way of saying that is a reflection over the x-axis. Which is a little bit weird because it seems like, okay, x-axis means horizontally. No, that's a vertical flip. It's a vertical reflection. It's the x-axis we are flipping over, and that's why it is vertical. And that 3 is a vertical stretch. Now, something that is worth noting. So my department, the math department at CU Denver has a Discord that we like to chat on. I think I mentioned this at the beginning of the semester. And even in that group of mathematicians and math teachers and everyone, there was several questions of, okay, what do we say that's a stretch or that's a shrink, or is that a horizontal or a vertical stretch? Because it's all, truth be told, kind of arbitrary. Like, I fully believe that you could argue a stretch is a shrink because you're kind of just visualizing it differently. Stretch is a very non-mathematical term. So instead of writing these weird things out, I mean, you can if you want to, and again, my math lab might be mean about it, I don't care as much about the wording. I care about the process. I want you to be able to transform these graphs. And so the wording isn't super important. What matters is what we're actually going to do to these key points. And so looking at what's happening here, if I didn't have all these terms memorized of, okay, reflection and vertical stretch or whatever, I would just say I'm multiplying my parent function by -3, right? That's what's happening there. And that's perfectly fine. You can say multiply y value make sure it is the y value because it's outside of the parent function. But that's a much easier way to think about what we're actually doing with our transformations. Yes, if you go carefully step by step and do your reflection and do your vertical stretch, you'll get exactly what we're going to get by smushing these into one step. I just feel personally that those words are overly verbose and not needed. And instead, we can just say exactly what we're going to do. Cool. And then what's my very last transformation? Oops.
Up 1.
Oh, 2 years. Perfect. Now we do the exact same process we did with our translations. We write down our key points, which are -1, 1, 0, 0. Cool. What's the first thing I'm going to do to all of these points?
Is it multiply by -3?
Nope. These are written in the correct order. So the first thing I'm going to do is this. So how do I do this?
You add 1 to your x values?
Yep. So I get 0, 1, 1, 0, 2, 1. Cool. What's my next step?
And you add 1 again for the y value. So what, like, so from 0, 1 would be 0, 2.
So you're right. I'm going to do that at some point. But again, I'm going to have to follow the order of operations. And that's the last thing, right?
So
It seems not like we don't have to follow the things. And yes, we will do up 1, but we have to go through this is 1, this is 2, this is 3, this is 4. We do have to follow our steps.
So you're going to multiply the y values by -3?
Yeah, exactly. I'm going to do this, which is I'm kind of cheating and doing 2 steps at once. If you want to do each step, that's fine. So I'm multiplying my y value by -3. Points will become 3, 1. Negative 3 times 0 is actually just 0, so that point's not going to change. And 2, negative 3. Now, who is helping me? Luis, what's my next step? Was it Luis? I think it was Luis.
Then do we go add 1 again?
There it is. Now we go. Now we do that last thing, order of operations. Add all these things. Just the y value. Again, if you're ever not sure, do I do this transformation to my y values or my x values? Think this is inside. The first step is inside, so I do those to my x values. These are all outside. So that's why I'm doing it to my y values. Just again, a good way to keep track of the things that you're doing. Okay, so this point becomes, let's go red, 0, negative 2, 1, 1, 2, 2. Great, those are my key points. Now what do I do?
You'd graph those points.
Won't you plot them on the graph?
Yep, exactly. Yep. So I take my graph. I put negative 0, negative 2, 1, 1, and 2, negative 2. And so again, now is where this sketch comes into play. I want to keep the same shape and I want to play connect the dots. And now I can't keep the same shape and the same direction, because if I try and connect the dots like this, there's not really a way I can hit all of those. And that's perfectly fine. And that also makes sense in the context of the problem, right? Because we said it reflects over the x-axis. So sometimes you just have to kind of flip your orientation in order to get your new graph. And now I would argue that graph would be hard for some people, maybe doable if you're really good at transformations, but very difficult for people to take the key graph and say immediately, that's going to be my new graph. But you can also kind of check it. You think, okay, I have my original graph, that's this black in black on the top right. And now did I move it right 1? Yeah, I mean, it's a little bit tricky to see that. Did I flip it over the x-axis? Definitely. Did I stretch it? Well, yeah, it looks like it got stretched or again, shrunk. The terms are kind of arbitrary. And then did I move it up 1? Yes. So it is a good idea to look back at these transformations over here to make sure they make sense. But as far as the process goes, this is highly recommended. There are other ways out there to do it. They tend to be much more difficult to track. Be good with that. Okay, one more example and then I'll let you loose to practice these. And again, the theme with mathematics is we like to say, okay, now hopefully you maybe kind of sort of a little bit understand how to take an equation and put it into a graph. Now we want you to take a graph and put it into a transformation. We want to write it as an equation. So that's what's happening here. This is an equation. It looks a little bit like a parent function. Yeah, this is Desmos, and Desmos doesn't like to do errors, but this would potentially go on forever, however, that direction. And so for starters, we need to identify our parent function again. So what does this generally look like? Which graph that we've seen?
Square root.
Yeah. So we can write it, why not? So I know at the end of the day, I'm going to have some sort of f of x is equal to the square root of x. Now, it's not a bad idea to sketch that graph too, kind of have a frame of reference. My absolute, or not my absolute, my square root graph looks something like this. And so now the goal is to identify what transformations are going to take this graph and make it look like this. It's not only that I'm bad at drawing, because that's Desmos, but what actual mathematical transformations are there? And so I recommend when doing these problems is identifying, again, a key point. And even better, if you can identify the lowest point on the graph or the highest point on the graph, then it's easy to track through with these transformations, right? Because let's say that you pick this point right here and say, okay, I'm going to track that point and see where it gets transformed to. Well, then over here, where is that? Is that here? Is that here? I don't really know where that actually shows up on my graph. Where if I try and start with the key point, no, the key point right here, oh, that's definitely this point. So how can I take this point and get it to this point?
Add 3 under the radical and then subtract 1.
Yeah, so it is left 3. It is down 1. And well, how does that look like when we're dealing with, that's a terrible one. How does that look like when we're dealing with these transformations? This is inside, so I'm going to, let's make a new function. Let's call it G. I'm going to left inside, so I'm going to go the opposite of what I would think it would be. Again, maybe in my brain. X plus 3, and then down 1. Now you might be thinking, okay, well, we just learned these two new transformations of this multiplying and this -1 flying around. How do I know those things aren't happening in this graph? And the kind of cheaty answer for this course is we're not going to do anything besides a translation, because that becomes a bit of up for debate of, okay, where did that second point go? Is that second point being stretched? So we typically just stick with, if we're taking a graph and writing the equation, we just stick with what are the translations. Is it moving left, right, up, or down? So you don't have to really worry about those reflections and stretches and strings. Again, I can't speak for my math lab, but as far as the exam goes, that is going to be the case. Cool. Any questions about that? Okay, so on the worksheet, I would do question 2 transformations. And then if you have time, do one of these graphs, the writing the equations, and then you can go ahead and call it a day. I have my office hours right after class, so if you need help on the homework or the test corrections, feel free to attend those, but otherwise you can head out. So James asked, why is it G? Great question, and this is me just kind of being very careful with my notation. When I'm writing up just mathematical equations, and I said right here, my parent function is this, I'm not really allowed to use that f of x unless it's the exact same thing. So all I did here was say, okay, well, I know my parent function is f of x. I'm going to be careful and say I have this new transform function. I'm going to call it G. You could call it H. You could call it R. Honestly, you could call it F and I would give you full points. But as far as just like strict from a mathematical notation things, we can't write 2 different f of x's on the same problem. Good question. Oh yeah, so Jackie asked which problems to do. So on the new worksheet, do 2 transformations. So do 2 problems that are like mouse, that are like this, taking an equation and actually graphing. And then if you have time, do 1 question like this. I'd prefer more on the transformation. So if you do 1 transformation and you're running short on time, practice the other transformation before doing this graph to equation type of thing. But hopefully you'll have time to do all of them. You got like 20 minutes. That's not unheard of, but always quality over quantity. Any other questions? Like I said, I might hop around to groups and remind you guys when the homework is, but also my math lab tells you when the homework's due. So just make sure you're kind of checking that on your own. Cool. Oh boy. Bad.